Good morning and welcome to our presentation on our airship that is set to compete in the CQ University annual airship race. My name is Lewis and I'm a civil engineering student. Our team consists of 2 civil engineers, Jared and myself, 3 mechanical engineers, Guy, Jordan and Matisse, and also 1 electrical engineer, Matt. To begin the design process of the airship, our team set out to create a well-detailed, in-depth project scope, outlining the exact scenario, expectations, inclusions, exclusions, and assumptions of the project. Some inclusions were, during the analysis of the towers, only the primary components will be taken into consideration. Bolt and rivet sizes will be excluded from research, calculations, and proposals. Also, dead loads will not be considered in the force, stress, and deflection calculations of the towers. Detailed aerodynamic calculations will not be considered, and detailed circuit analysis will not be conducted on the electrical subsystem. An assumption we will be making is that the budget is not a major issue but will be minimised where possible. Thorough research into different designs, flight methods and materials were embarked on for both the airship and the docking towers, as well as detailed and accurate calculations determining aspects such as weight, buoyancy, control, and structural integrity. Each design the team come up with was systematically and meticulously weighted against each other in order to find the fastest, most practical, most supreme overall airship and tower design. The first and most important step to initiate was the project plan. The plan was used throughout the project and was designed in the beginning of the project phase to be as accurate and easy to follow as possible. Our team arranged a meeting and created this plan coherently. We created our project plan in the form of a Gantt chart by using Microsoft Project and split the entirety of the project up into more manageable sections. The first being the planning phases, in which all team members were available to take upon all tasks. It was important that our communication remained strong through this part of the project to ensure that we were all keeping along the same track. The plan went on to first include execution, which encompassed the research for the towers, airship and systems, all done by allocated team members as seen in this PowerPoint presentation. Second was the evaluation, thirdly was the calculations, and lastly we had the closing phase, which we worked on the proposal and thoroughly reviewed it. Now I'm going to introduce Jared to talk about some civil aspects.
Hi, I'm Jared and I'm looking after part of the civil aspects of this project, the towers. After conducting research into various different tower structures and truss designs, we came across 2 designs which we felt could be viable for our project. The first design is called a 4-chord truss or a box truss. The box truss is quite a simple design which consists of 4 large members or chords arranged in a square-shaped formation, connected on each side by zigzagging smaller members or webbing. The second design is a 3-chord truss or triangle truss. The triangle truss design is quite similar to the box truss, except that it only has 3 chords arranged in a triangular formation. Once again, these chords are joined by zigzagging webbing. While comparing these 2 designs, the 2 key criteria we considered were the strength and stability. In accordance with these 2 criteria, the design we decided to go with was the box truss, as it is superior in both of these areas. Another advantage of the box truss is its simple design, which makes it easier to analyse. Having said this, we do realise that the box truss is heavier and more costly, but we have evaluated these downsides and have come to the conclusion that the benefits outweigh the disadvantages. In order to combat having chosen the heavier and less manoeuvrable box truss design, we have decided to incorporate a mechanism for separating the tower into 2 halves, making it much easier to transport. The design incorporates a sleeve that slips over the top of the legs on the bottom half. The legs on the top half then also slide into the sleeves and are pinned in place to hold them in position. In regards to tower sizes, we have decided upon a tower height of 2 metres and length and width of both 0.25 metres. Sizing the towers to these dimensions means that they are large enough for our purposes, while still being a manageable size if we are required to relocate the tower indoors in the case of poor weather conditions. When considering which material to use for the towers, the criteria we took into consideration were strength, weight, and cost. Having based our decision on these three criteria, we came to the conclusion that aluminium is the material that would best suit our needs. This is because aluminium is lightweight and cheap. However, in regards to strength, aluminium is not as strong as some of the other options such as steel or iron, but we believe it is strong enough for our purposes, while having the previously mentioned advantages. This sums up my section discussing our design plans for the towers. I'll now hand over to the mechanical engineers to discuss their sections of the project.
Hello, my name is Matthijs. I am participating in the mechanical aspects of this project. I am responsible for three of the aspects involving the airship design project. These aspects are the method of applying the gas to the airship model, the design conformance to Australian standards, and the control surface to steer the airship horizontally. I am assigned the task of proposing the most effective method of applying the gas inside the airship. The chosen method of applying gas to the airship was via a car valve that allows gas to be injected inside the airship without it being able to escape. Car valves are widely accessible and are therefore a relatively cheap alternative for allowing gas to be applied to the airship. The external source of the gas is out of scope of the project at this stage. However, it is a pending problem for further design. The project also needed to regard a number of standards to avoid any unforeseen conflicts with stakeholders. Since the model will be operating in the air, the Australian Civil Aviation Safety Authority standards had to be considered. According to their standard AC 101-3, the airship should not exceed a height of 400 feet within 3 miles of the aerodrome unless permission has been granted by the appropriate air traffic control service or CASA officials themselves. Other standards that need to be considered is the Australian Design Standards for Technical Drawings. This will allow any confusion between the model specifics and the design drawings to be eliminated. Finally, the airship also needed to be able to be controlled, and therefore a design service needed to be included. I'm responsible for making sure that the control service is capable of influencing the course of the airship so that it reaches its target quickly and safely. The designed control surface is somewhat similar to a vertical stabilizer seen on aircraft. It features a large vertical fin at the rear of the airship that would rotate left or right to steer the airship left or right respectively. I will now hand over to Jordan to further discuss any mechanical aspects.
Hi, my name's Guy, and I'm another mechanical engineer, and I've taken on the process of, we looked at an accelerated launch. So the idea was that we were going to shoot this thing well into the race distance and then fly it, shoot it as a projectile well into the race distance and then fly it as an airship from that point on. So it would have made the airship a bit more complicated, having to become buoyant at some period in the race without being buoyant at the beginning. We considered using a trebuchet, a catapult, slingshot as a means to accelerate it, which we wiped out because that was a mechanical method of propulsion and we had to use electrical. So we decided to look at a railgun, which NASA gets projectiles up to 10 times the speed of sound with. We ended up walking away from an accelerated launch, mainly due to safety concerns for spectators and the other competitors in the race. Then I had to go on and look at current designs that were available, and there was rigid, non-rigid and semi-rigid. Rigid designs are basically an outside frame that the gas envelope sits inside, and that was generally for really big, heavy weight airships, and so we've moved away from that to a non-rigid design and just using the envelope that holds the gas as a means of where to make up our main structure. And following the main structure, we had different types of designs we could use. Like a double hull, which would reduce the length of the design to give you the same amount of lift. A lenticular design, which is okay for hovering type things, but not real good for moving forward. And we also looked at having wings on the design, but they increased drag in some circumstances up to 60%, which was another thing we didn't want to do, because we wanted the design to be sleek and efficient through the air. Then I moved on to propulsion systems, and we looked at a cycloidal rotor, which allows the airship to move in any direction, because all you do is to change the angle of attack of the small wings, and that will let it move anywhere around. We considered a ducted fan, propeller, or a rim-driven fan. Ducted fan and rim-driven fan are very similar, except the rim-driven fan takes out the need for torque compensation on the airship, and the propeller is generally the way we decided to go, because it adds on a hell of a lot less weight and it's quite easy to drive. And I'm now going to hand over to Jordan, another mechanical engineer. Thank you.
Hi, I'm Jordan, and the majority of my work towards the project is in the areas of buoyancy and ballast controls. I have two key responsibilities. One is to keep the airship as stable as possible while it's travelling through the air. The other essential function is to enable the airship to be able to rise and descend. From researching various designs for these systems, the most suitable and simplistic design was chosen. This design allows the buoyancy controls and the ballast controls to be combined into one system. This will be achieved by changing the amount of air that is present. This change in weight can be controlled so that the airship can either rise, stay at a constant height, or descend. Use of this control system involves a pump with air valves to direct the air flow as necessary. This allows air to be transferred into two separate locations within the airship, one in the front and one in the back. By utilising this design, the ballast aspects can also be controlled, as the air can be pumped or removed into either or both sections at any time. I'm currently investigating a method to make the ballast controls an automated system to improve on its effectiveness. I'll now hand over to our electrical engineer, Matt, to continue the presentation.
Hi, I'm Matthew, who looks after the electrical aspects of the project. I'm in charge of all electrical elements, including power requirements, generation and storage involved with the airship. Extensive research has been done surrounding electrical motors, solar PV panels, batteries, control systems, and all the specifications of these elements. Through the research that has been conducted, it was found that factors are involved for appropriate selection criteria of the components were required. The power requirements of the airship mainly is drawn by electric motors. The selection of electric motors was done ensuring maximum efficiency, a compact design and lightweight to guarantee the minimum effect on the overall weight of the airship. The solar PV panels were selected using the criteria of that light yet efficient panel to be selected. From conducting extensive research surrounding batteries, it was found that the correct batteries for the airship and the tower were lightweight batteries that have high capacity. The control system for the airship has been designed to allow for the most precise flying experience, with having the most advanced system on the market, allowing the user to adjust the flight path by as little as 2 degrees. Combining these components ensures that the user will experience the most elegant and functional airship that is currently available. This concludes our presentation, and thank you for listening.